Every time an artificial intelligence model learns, billions of calculations race through specialized computer chips. Massive server rooms filled with processors train language models, generate images, and analyze enormous data sets. Yet behind many of these systems sits a technology most people rarely think about: Nvidia's graphics processing units. For years, Nvidia was known mainly for gaming hardware. Its chips powered graphics inside personal computers, rendering complex environments in video games. But what looked like a niche market eventually became something much larger. The same architecture designed to render images turned out to be perfect for a new type of computing problem. Artificial intelligence requires enormous parallel calculations. Instead of performing one task at a time, AI training systems run thousands or millions of operations simultaneously. Graphics chips were originally designed for exactly this type of workload. Rendering a game scene means calculating thousands of pixels at once. That overlap created a surprising opportunity. While most semiconductor companies focused on traditional processors optimized for sequential tasks, Nvidia continued improving graphics hardware capable of massive parallel processing. The architecture evolved into a highly specialized computing engine. In the early days of the company, gaming drove nearly all demand. The graphics card market rewarded companies that could render higher resolution images and faster frame rates. Nvidia competed fiercely with other chip manufacturers for dominance in the gaming ecosystem. Yet inside research labs and universities, something unexpected was happening. Scientists began experimenting with graphics processors for complex calculations unrelated to gaming. Simulations in physics, chemistry, and machine learning ran dramatically faster on GPUs than on traditional CPUs. At first, these experiments were limited. GPUs were difficult to program for non-graphics workloads. Developers lacked tools to fully harness their potential. Nvidia recognized this barrier early, so the company built a software layer. In 2006, Nvidia introduced CUDA, a programming platform allowing developers to write software directly for GPU computing. Suddenly, researchers and engineers could design applications that used thousands of GPU cores simultaneously. What once required complex workarounds became a structured programming environment. This decision quietly changed the future of computing. CUDA created a developer ecosystem. Universities taught GPU programming. Research teams optimized algorithms for parallel processing. Machine learning frameworks began supporting GPU acceleration. As more software relied on CUDA, the Nvidia ecosystem strengthened. But the real turning point came with artificial intelligence. Deep learning models require enormous training power. Neural networks process vast data sets to identify patterns and relationships. Training one model can involve trillions of mathematical operations. GPUs turned out to be ideal for this workload. Researchers discovered that training neural networks on GPUs could reduce training times dramatically. Tasks that once required weeks could be completed in days or even hours. Suddenly, demand for GPU computing exploded. Technology companies building AI systems needed massive amounts of processing power. Data centers filled with racks of GPU servers. Large clusters connected thousands of processors together. The architecture Nvidia had spent years refining suddenly became the backbone of a new industry. Yet hardware alone was not the full advantage. The software ecosystem surrounding Nvidia's chips continued expanding. Libraries, frameworks, and development tools allowed engineers to build increasingly complex AI systems. Major machine learning platforms integrated directly with Nvidia GPUs. Training pipelines optimized automatically for GPU clusters. This ecosystem created a powerful form of lock-in. Developers invested years optimizing their models for CUDA and GPU acceleration. Switching to a different architecture would require rewriting large portions of software infrastructure. As a result, Nvidia's platform became deeply embedded inside the AI research community. But the scale of infrastructure required for modern AI is staggering. Inside large data centers, rows of server racks house clusters of GPUs connected by high-speed networking systems. These clusters act like giant supercomputers dedicated to training artificial intelligence models. Cooling systems regulate heat generated by the processors. Fiber networks move enormous amounts of data between nodes. Each new generation of AI models requires even more computing power. Training advanced models can involve thousands of GPUs operating together in synchronized clusters. The scale resembles scientific supercomputing projects more than traditional enterprise servers. Nvidia adapted its strategy to match this demand. Instead of only selling individual chips, the company began designing complete AI computing platforms. Integrated systems combine GPUs, networking technology, and specialized software optimized for large-scale machine learning workloads. Data center operators can deploy these systems as building blocks for AI infrastructure. However, this is where Nvidia's position becomes especially powerful. The company operates at the intersection of hardware and software. Its GPUs power the computations. CUDA powers the developer ecosystem. Machine learning frameworks integrate deeply with its architecture. Each layer reinforces the others. The more developers optimize for Nvidia platforms, the more valuable the hardware becomes. The more data centers install GPU clusters, the more software tools emerge to support them. This creates a reinforcing ecosystem similar to other major technology platforms. Yet even dominant infrastructure systems face challenges. Artificial intelligence workloads continue evolving rapidly. New chip architectures appear regularly. Other semiconductor companies are exploring alternative approaches for AI acceleration. Specialized processors designed specifically for machine learning may reshape the landscape over time. Energy consumption also raises questions about future scalability. Large AI clusters require enormous electrical power and cooling capacity. Data centers must balance performance with operational efficiency as models grow larger. Still, Nvidia currently occupies a critical position in the AI infrastructure stack. What began as a graphics chip company quietly became one of the most important computing platforms in the modern technology ecosystem. GPUs that once rendered video game environments now train the neural networks powering language models, autonomous systems, and scientific research. The shift happened gradually. Gaming hardware evolved into parallel computing engines. Parallel computing engines evolved into AI infrastructure. And the software ecosystem built around those chips transformed them into a platform used across the entire technology industry. From the outside, Nvidia still looks like a semiconductor manufacturer, but underneath it operates something much larger, a global computing infrastructure layer powering the rise of artificial intelligence.